So hi everyone, my name is Valli. Today I'm going to be talking about a project that we've been working on at the AI Engineering and Health team at Vector that I'm really excited to share with you all. And it's called CyclOps. So we're all here to talk about enabling the responsible deployment of machine learning models in the clinic. There are several barriers right now that are associated with deploying clinical models. Some of these include things like a lack of standardization in clinical data, model and data biases that are left unaddressed, and a lack of processes for model updating and monitoring. And so our team wanted to tackle these challenges using MLOps best practices in order to accelerate the deployment of clinical machine learning models. So CyclOps stands for Cyclical Development Towards Operationalizing ML Models for Health, and we wanted to target all aspects of the MLOps cycle. So starting from data, from formulating the problem, defining your inputs and outputs, building a data pipeline to actually building your model, formulating the representations, training your models, analyzing the performance to actual deployment, creating an inference pipeline, and then doing the evaluation and monitoring processes. Our aims are threefold: to accelerate ML workflows using MLOps best practices, like I mentioned, enabling development of sophisticated ML models, so reducing the amount of time it takes for data cleaning, data processing, the really tedious steps in building the model, and then facilitating the rigorous evaluation and monitoring of these models using state-of-the-art drift detection and custom evaluation metrics that are specific to the clinical context. So a bit of an overview, what we've been working on, where we are, where we're going. So prior to this, we were working on our querying API, our processing API, and we started working on some use cases. And we started with our drift detection experiments. Now we've done OMOP integration. We have a drift detection API, a processing and querying API, which I'll talk about these a little bit more, as well as multiple use cases with our collaborators. And then for January, we want to finish our evaluation API and a delirium production use case with GEMINI. So the key features in APIs of CyclOps include an extensible querying API for EHR data sets, a modular and extensible processing API for static and time series data, a drift detection API, and a front-end non-technical interface. So I spoke about how one of the problems or barriers for the deployment of clinical machine learning models is this lack of standardization in EHR data. So the OMOP Common Data Model is a standardized schema for standardizing the structure and content of observational health data, and it uses common representations and terminologies, vocabularies, things like that. So it's really important that we support OMOP integration in our querying API. So our CyclOps querying API does support OMOP integration, whether that be a custom data set that you have, or a Mimic, or for GEMINI. But also, if you maybe don't have data in the OMOP data format, you have a favorite data set that you want to use, you have your own data that you want to use, you can still use our high-level querying and API functions. And so the idea is you query your data, you get these nice data frames. And then it goes through a data pipeline. So we have a structured way to actually clean the data, which is then sent to these two classes, processed into two classes, a tabular features class or a temporal features class, which are then sent to our computer aggregator with many different functions you can choose from, which then spits out our vectorized data format for our modeling in our feature store. So now you have your data, you maybe built a model. One of the other barriers that I discussed was data distribution shifts in clinical data. And in clinical data, this occurs across various different ways, whether that be technology, differences in EHR systems, population setting, changes in demographics that result in these data shifts, or changes in behavior, whether that be at a patient level or at a physician level, through events that are happening just in the real world, or new reimbursement incentives or policies. It's really important to identify these shifts and address them in a label-agnostic manner. So we built a drift detection pipeline in order to enable that. So the idea is, in the event that you don't have labels in many situations can be very costly and resource intensive to acquire. You can actually use the data and the model that you have and actually play around with the types of shifts that could occur in real life, as well as synthetically induced ones, and evaluate how that affects your model's performance. So you get your data from your feature store. We have a shift applicator class where you can apply these types of shifts. You can look at shifts across different institutions, across different time points, across sensitive attributes, as well as synthetically adding noise. And then you get your source and target data, which you can now do different experiments on, whether that be looking at drift detection over a rolling window, or doing sensitivity tests and evaluating how much of your target data you actually need to detect drift in your data. And this is all done by our drift detector, which consists of a reductor to reduce the representation of the data and a tester module. And so then you get a drift alarm, and this can actually trigger your downstream retraining processes, which is something we're working on. So I'm just going to showcase some experiments that we've done in 2 use cases. The first is a collaboration with GEMINI. Most of our framework building has been in the GEMINI context. So GEMINI is this collection of data from the general internal medicine wards of hospitals in Toronto. And so in this experiment, we're using EHR data from the general internal medicine wards from 7 hospitals, 5 academic, 2 community. And this is just, again, an overview of our processing pipeline. So we just extracted the data, we imputed missing features, aggregated, and we have these patient profiles we can now use for modeling. So we built a mortality decompensation, all-cause mortality decompensation prediction model. So basically predicting whether a patient's health will deteriorate and result in in-hospital mortality within the next 2 weeks, every 24 hours of their stay. This isn't the main point, this is more just to kind of give an idea of the performance of our model for the downstream experiments. So here you can see the sample sizes for our training and test set, and then the AURC and the AUPRC for our model. We can also look at within specific diagnosis chapters how our model does. So for certain diagnosis chapters like the circulatory system, diseases of the circulatory system or the respiratory system, our model seems to be performing better on compared to others. And now we can also evaluate across, drift across different real-life trends, events, and demographics. So here, I'm taking this data and we've trained our model on community hospitals. And then we're evaluating now on community hospitals as well as our out-of-distribution data, which are academic hospitals. You can see that there's a clear model degradation when we evaluate on our out-of-distribution data. And that's also, we were also able to detect that using our drift detection algorithm. So you can see that in a label agnostic manner, the red line actually goes below the p-value threshold, and we're actually able to detect that there is a drift and that there will be model degradation in a model agnostic manner or a label agnostic manner. We can also do this across seasons. So here's a model trained on all the months excluding summer, and then evaluated on both the in-distribution data and the out-of-distribution data. And here we actually don't suffer from a model degradation, but we're also not detecting drift. So that's nice to see as well, that the opposite end of it, we're also able to detect these negative events. Another example is demographics. So say we train a model on only males, and then we evaluate that model on females. We can see that that model now, this mortality decompensation model, suffers from model degradation. And again, we're able to detect that difference using our drift detection. Here's a kind of a simulated deployment setup that we did. So here, trained a model on all the data prior to 2019, and now we're evaluating that model as well, their performance metrics for the model, as well as the drift metrics across time from 2019 to August 2020. And so all the red highlighted areas are where we actually see a significant drift. The dotted line there actually is when Ontario entered a province-wide lockdown. And you can see that we actually do detect a drift that, in a label agnostic manner that actually changes the performance of our model at the time that Toronto entered the lockdown. We can play around with things like sensitivity. So if we reduce the number of patients that are used in our statistical tests, we can see that it actually reduces our sensitivity to detect this drift. And these types of experiments are really important to conduct in a real-life setting. And we hope this will also facilitate the development of retraining strategies. So a lot of our speakers today already kind of hinted at that, talked about that a little bit. So by doing these simulated deployment setups, we can actually evaluate how our model, the performance of our model over time when we try out different retraining strategies, playing around with different things like window size, the drift threshold, for actually triggering the retraining. Our second use case is a collaboration with THP, Trillium Health Partners, for chest X-ray data monitoring. And so in radiology, ground truth labels are really expensive. They're time-consuming, resource-intensive, and medical imaging is a really highly dynamic domain in terms of changing pathologies, changing devices. And so this is an application of drift detection that's really important. So using our same pipeline, this is kind of our overall data set that we were working with. There's 3 distinct time periods that we broke up our data from 2018 to around the end of 2020, each about 8 to 10 months, each consisting of about 50,000 chest X-ray scans. And so that green period is kind of our control period. The yellow is our pre-COVID period, and then our red is when COVID was happening or when we were in that lockdown. And so you can see when we compare the pre-COVID shift to the COVID shift that there is a more significant shift during COVID. We can also look at this at an institutional level, so between the 2 hospitals, between Credit Valley and Mississauga, we can see that a Mississauga hospital seems to be more susceptible to this shift compared to Credit Valley. We can look at this in the context of the ICU versus outside of the ICU. Outside of the ICU, again, the shift from COVID seems to affect the model more than it does in the ICU context. And again, across different attributes like gender, patient class, hospital, and age. So here on the x-axis, we're increasing the amount of the out-of-distribution data, and we're seeing how much more shift there is. And so, for example, in the age plot, you can see that certain populations seem to have a greater effect on the distributional shifts of the model. So in this case, it seems like younger populations seem to actually shift the model more than older populations. So our goal is to build kind of these multiple reusable implementations. These are some of the ones we've already built, from mortality prediction to prolonged stay in the ER to chest X-ray data monitoring, and now working on delirium prediction. And there will be much more to come. But one thing I want to highlight is this would not be possible without all our collaborators, all our partners. Partnership has really been the key to success for CyclOps. And so if you're interested in trying out some of these experiments that I talked about with your own model, with your own data, this is an open source framework, and we're happy to collaborate with all of you guys to try out these experiments on different patient populations with our industry partners and with hospitals for real life deployment situations. So thank you.